Today we're going to be talking about potential energy diagrams. Potential energy diagrams are energetic diagrams that demonstrate the changes in energy through the course of a reaction. There are two axes on a potential energy diagram. The y-axis shows potential energy. Potential energy can actually be given in numbers, or on this example, values aren't given at all. We're just assuming that higher on the axis are larger amounts of potential energy. The other axis, the x-axis, shows the reaction coordinate. This is often also shown as time. All this means is it's just allowing you to see the progress of the reaction. There are several parts of one of these diagrams that you need to be able to identify. The first part is the potential energy of the reactants. It's shown on your diagram by the letter A. The potential energy of the reactants is the energy held by those molecules before they have reacted. The second thing you need to be able to identify is the potential energy of the products. This is shown by letter B on your diagram. Just as the potential energy of the reactants is that energy that the starting materials are holding, the potential energy of the products is the energy of the ending materials in a reaction. The activated complex is a high energy state that occurs in the middle of every reaction. This can also be identified as a transition state. During the activated complex, atoms and molecules are rearranging, and the original broken bonds are trying to form new bonds to make their products. Potential energy of the activated complex is represented by C, and what this is showing us is the amount of energy that the intermediate materials have during this reaction. In order for a reaction to occur, our initial reactants must actually get enough energy to overcome that barrier of the activated complex. My activation energy is going to demonstrate that amount of energy. My activation energy is from where I'm starting, is the amount of energy it's going to take to get up and over the energy hill. So in order for this reaction to proceed, I must get up and over my activated complex. In order to do that, I need the amount of energy between where I started at A and this high energy state C. So that amount of energy is represented by letter D. Activation energy can be seen in a lot of things in our day-to-day life. One of the things we've seen with activation energy a lot in class is the starting of a Bunsen burner. If you simply turn on the methane gas, nothing will happen. Lighting the match provides the activation energy that takes my initial starting reactants up over that energy hill. Finally, the heat of the reaction, which we also refer to as delta H, or change in heat, is the net amount of energy that is going to be either given away or absorbed by a reaction. So this is an overall net energy change in the reaction. So this net energy change in the reaction doesn't have anything to do with your activation energy or your activated complex. This is simply the difference between the amount of energy you ended up with. So where I ended up here is B, my energy of my products, and where I started, my potential energy of my reactants. So this is shown on my diagram by E. This can also be solved by doing B minus A. The order in which you subtract these is very important because we want to actually also tell people if the reaction is exo or endothermic. So it has to be our ending material minus our starting material. And there is a sign convention with this. Your delta H will always be given with a positive or a negative sign. So this particular diagram right here, we can see that the amount of energy of our starting materials, or our reactants, is higher than that of our ending materials. So when we do our B minus A in this case, since B is a smaller number than A, that's going to give us a negative value for this reaction. Whenever you have a reaction where your delta H is negative, this is considered an exothermic reaction. So my delta H, my heat is going to be released in this case. In other words, the amount that I started with is more than the amount that I ended with. I gave the rest of that away. So that's going to give me a negative delta H. We're also going to look at some endothermic reactions where you're going to see that overall you're going to have a positive delta H. In other words, this system is going to absorb energy. And as I mentioned again, the diagram above is for an exothermic reaction where heat is being released. Now I do want to clarify one thing. In all reactions, there are two major steps. There's a first endothermic step. What this initial step is talking about is the fact that from the amount of energy we are starting with, we always have to go up over this energy hill. That is an endothermic step. After we've gotten up over that hill, as new bonds are forming and products are being made, we have an exothermic step where energy is being released. Now, in a reaction overall, whether or not the reaction will be exo or endothermic has to do with the net energy changes. In an endothermic reaction, the first step requires more energy than the second step releases. In an exothermic reaction, the second step releases more energy than the first step required. If we wanted to show a potential energy diagram for an endothermic reaction, where energy is being absorbed, this would look fairly similar to the one that we have for the exothermic reaction. We'd start with our energy of our reactants, go up over our activated complex. However, we don't come back down quite as low. So we have our potential energy of our reactants. We have our potential energy of our products. We have our potential energy of our activated complex. Our activation energy, in order to get up over that energy hill, is represented by D. And finally, if we were going to determine our potential energy our heat of our reaction, we'd be doing B minus A again. When we do B minus A in this particular example, B is larger. Therefore, we're going to get a positive delta H. Exothermic reactions always have a negative delta H. Endothermic reactions always have a positive delta H. Because this graph ends higher than where it started, that's telling you that this system absorbed energy and has more than it started with. So in this particular case, what makes this diagram different from the exothermic reaction, if we look back on our exothermic reaction, we ended up at a lower energy. In an endothermic reaction, our products will be higher than our reactants. And we're going to have a positive delta H, since this is endo. You're going to be doing a couple of examples of reading these diagrams, so I'm going to walk through one with you to get you started. When we're reading one of these diagrams, we start by always doing our heat of reactants first. Heat of reactants are shown by where we're starting. In this case, our starting line right here is at 60 kilojoules. Our ending amount of energy, our heat of our products, is shown right down here at 20 kilojoules. activated complex, our very highest spot that we had to get to on this graph, shown right up here, 100 kilojoules. For our delta H, remember we're doing where we ended up minus where we started. We ended up at 20. We started at 60. So for our delta H, it's going to be 20 minus 60. If you had done 60 minus 20, you would still get the same value, but you would have the wrong sign. This is going to give me a delta H of negative 40. The negative is what tells people that this is an exothermic reaction. So my reaction will be exothermic. I can tell this because I'm ending at a lower place than I started. When I'm trying to remember which way delta H goes, I often think about my bank account. If I had started the month with $60 and ended the month with $20, I would have a negative change in the amount of money that I had over the course of the month. Delta H has absolutely nothing to do with activation energy. No matter how much money you have in the middle of the month, even if you had $100, if you only have 20 at the end of the month, that's all you got left. Last, we've got our activation energy. Our activation energy, remember, is the amount of energy it takes to get us over our initial starting energy barrier and get this reaction started. Our reactants have 60 kilojoules. They have to get up to 100 kilojoules. In order to make that energy leap, they need a total of 40 kilojoules. Activation energy is probably the most easily confused part of reading one of these graphs. Keep in mind, all reactants are going to have some starting energy, and you just need to consider what it would take to get them over that energy hump. This is all you need to know about reading potential energy diagrams. Please complete the rest of the worksheet, and Mr. Couliard will go over the answers with you.